and let me know when you can see it.
Okay, I see it.
Okay, so when you first start up ChromaTrace, this is how it pops up. First of all, ignore this update available. For some reason, it's currently not working, so just ignore it for now. So when we
Okay.
start a new project, come over here to the far left and click New. And this gives us a chance to um, start a new project. And so we'll open one up. Takes a second, and it creates this project. Boom. So the first thing it does is it populates with one line and no
Hmm.
tanks yet. So this is where we set up this very first line. This is where you can put in your line number. If it's associated with a parent line, like it's teeing off of a parent line, we can indicate that in here and it'll adjust for it. But just to get started, let's leave it exactly how it is and call it a 2-inch line. And we'll start filling out these tables. For very first thing I always do is get rid of that 10% and go to 20. Um,
Okay.
we'll default to 20 in a future revision, but for now, 20. And the reason I do that is always keep in mind Ohm's law. You know, power equals current times voltage. So if we have a voltage drop, we have a power drop. And we have voltage drops. There's one huge project that was a concentrated solar project up in Nevada, and they didn't allow for the voltage drop that they encountered. And they consistently froze up and caused all kinds of problems, but it was primarily voltage drop that got them. So one way to not have voltage drop impact your heat trace system is to put your heat trace on a dedicated transformer that's got adjustable taps. So if the plant has a voltage drop in the plant, wherever the transformer is getting its power, you can go in and adjust the transformer and bump its voltage up. So super important. Next
Okay.
one is the maintain temperature of the top. That's the temperature we're going to keep the pipe at. So for freeze protection, some people call out 40 degrees. I recommend 50 if you're anywhere where it's consistently cold. What do I mean by that? Well, we'll jump over to Central California, Fresno. It's not consistently cold there. It might drop down to 20, 15 degrees at night at the coldest time of the year, but then the sun pops up and it gets warm pretty quick. So there I might go to 40 degrees. So,
Okay.
but basically 40 to 50 for freeze protection. If you want to be safe, leave it at 50. That's why we default it. The minimum ambient, this is where people get this wrong all the time. And the minimum ambient is the absolute 20-year minimum ambient, not average minimum. People use average all the time. That will bite you. You want to design for worst case scenario. So that's absolute minimum ambient. And you can typically find that data searching the internet. If you're not sure, you can ask your customer for it. But in your case, you're probably going to have to educate your customer. So that's minimum
Yeah.
ambient. Yep. All right. So
Okay.
startup is the temperature that you're going to start the system up. So if we're in Nome, Alaska, we're going to design at a minus 60 minimum. And we're going to design for a startup temperature of minus 60 because it's going to stay minus 60 all day, all night in the dead of
Okay.
winter up there. However, if we're back to Fresno, California, we might do something like this. We may do startup at 50 because as soon as the sun pops up in the morning, by 10 o'clock, it's 50 degrees every single day or warmer. So the reason for startup is self-regulating heat trace has a very high inrush current, and we
Hmm.
have to design for the inrush current, not the operating current. But these are both come in play. So if you're not sure, put it at the same temp as your minimum ambient.
Okay.
All right, maximum ambient, again, depends where you're at. If you're not sure, you can default at 110. If you know you're going to Phoenix, Arizona, certainly you want to bump it to 120.
Okay. And then that's going to be the same as the minimum ambient where we want to get the absolute, not like a 5 year
Yep,
average
yep,
or a 20-year average.
yep, you're on it.
Okay.
Absolutely. Yeah, so you got that. And then now the next few things get fairly critical. And this is the temperature that the pipe is going to get exposed to. So what does that mean? It means if you're cleaning out the pipe with steam, you need to know your pounds of steam for your maximum temperature. And the reason we do that is this helps select the right fit cable. So let's say this was 600 degrees. If I put in, we're going to run 600 degrees down this line, right off the bat, it gives me an error message and it says that the pipe temperature is too high for a self-regulating cable. So we have to go in and pick a different kind of cable, and then we can get rid of that. Now it's just telling me I need to have control on it. I'm going to put these back. So this is a real critical item right here, that we put the right maximum exposure temperature in, because that's going to help us choose the right cable. It's going to have the software choose it for us.
Okay. And then so touching on things like the maintenance temperature and the maximum exposure, who is it that I would be getting that information from? Is that my process team
Yep.
or the customer?
No,
Okay.
it's in your case, because you guys are doing digesters. You guys are going to be the experts. The people that own dairies are not.
Okay.
Yep. So you're going to be talking with your process people and figuring, what it is. So sometimes you guys do have 200-degree exposure temperatures, and then that'll change what cable's called out. So this stuff is from your process people. You might even build your own little um, sheet for checking these off. I have some design aids for you. We've probably given them to you before. The worksheet. What I like better than the worksheet is to use a spreadsheet for all the lines, because then you can upload that directly into ChromaTrace without doing a bunch of keystrokes.
Yeah.
I'm gonna follow up and get both of those to you again, so you have them in one email. I'm gonna make notes as I go, and I'm
I'm
gonna
doing the same.
Yep, and then I'll send you an email that has all the stuff in it as we've talked about. So hopefully that's pretty explanatory up there. And the line number is just your line number off of your own line list or your isometrics. Now we drop down into voltage. So higher voltage is always better with heat trace.
Of
Again, it comes
course.
back to Ohm's law, right? Power
Hmm.
equals current times voltage. You want higher power, you have higher voltage. You go higher voltage, you get lower amperage. Lower amperage is what you're looking for, because that will reduce your circuit counts. It'll lengthen your circuits. So we really like to use 277 in the industrial world. Most people have 484 wire. Well, we get to pull one of those three legs and use it at 277. Maximum breakers. This is really has to do with what your company feels comfortable with doing. Some refiners, they only allow a 20 amp maximum breaker. And again, you only get to use 80% of that because of
Hmm.
National Electric Code NEC. So if you can go up to 40 amps, again, you can reduce your circuit counts. So real important.
So while we're talking about breakers, there was something I was wondering about when I was watching that video yesterday. So if I have a dedicated heat trace panel,
Yep.
I believe all of the circuit breakers in that panel have to be GFEP, right?
Correct. Or it has to have electronic GFEPs. So some of our full feature set controllers, um, on the low end of the spectrum is our ITCs. They come in 1 and 2 circuits. On the high end is our ITLS, ITAS, depending if it's line sensing or ambient sensing. So those have ground fault protection built into the panels.
Okay. And then so for the main circuit breaker for that panel, does that
Mm-hmm.
also need to have the ground fault protection, or can that
No,
just be like, okay.
no, no. So
Yeah, because that was
it
one thing
does
I
not.
wasn't sure about. I was like, it makes sense that it doesn't need it, but I don't want to start off with a wrong assumption.
Yep. No, this is awesome. So, um, and if you're not using a full feature set panel, then whatever is feeding the control device you're using, and the control device can be a breaker. Step up the next step can be a T-stat, and those come in, bulb and capillary T-stats. They come in line sensing and ambient sensing. And then the next step up from that, we're typically getting into a digital control of some sort. So if the controller doesn't have ground fault protection in it, then the breaker feeding the device must have it. But either way, all heat trace in North America must be protected with ground fault interruption.
Okay.
All right, so as we move over here, if you saw when I put the temperature real high, I put it high enough where I knew you could use self-regulating and it gave us an error message, so I changed it to a different cable. This is where we pick our cables, and 85% of all heat trace is done with parallel self-regulating. And then we can pick different families. So when we go into the families, it's best if you let it pick it.
Okay.
But there's a caveat in there. So if it's a freeze protection, it's typically going to pick SRL. If it requires a little higher maintain temperature, it'll slide into SRP. I personally do not like SRP cable. It's hard to work with. So when I can, I only design with SRL or SRME.
Okay.
The way you can remember that is when you get down here, we only make hazardous SRL and hazardous SRM. The only time you would use SRP is in a class 1 um, div 2 scenario or a class 1 div 1 scenario where the auto ignition temperature, it will cover some of the bases that SRME won't. But I've never seen a failed piece of SRME cable. I have seen failed SRP, so I personally I don't like to design with it. So um, we would get rid of it, but it does fit some niche applications. So just be aware of that. If it puts in SRP, go in and override it with SRME and see if you get an error message. If you don't, keep it with SRME.
Okay.
So the other thing you can do is you can pick cable models. So what you don't want on a project is 5 different cable models because your construction crew won't keep them separate, or they won't keep track of them. So for constructability, I try to narrow down to 2 cable sets. And if you're using ambient control, you got to be a little careful with that you're not overheating the lines. But if you're using line control where you're actually measuring the temperature of the line, it doesn't matter if you have a little too much power on it. The controller will take care of it. But just think about that in constructability. If you had it calling out some 3, some 5, some 8, and some 10, you might want to go in and just use 5 and 10 on it. And you can go in on a per line basis and you can drive that right here.
Okay.
Also, if you're using polymer lines, you want to go in and tell it that you're putting aluminum tape to attach it. If you're using steel lines, you use fiberglass. If you're using MI heating cable, that's the little metallic heating cable that looks like brake line off a car, you would pick the stainless steel. So you have to tell it how to attach it. It usually will pick it correctly itself, but I always like to just go in and double check that.
Okay.
All right, here's where it get interesting. So sometimes you run into cases where they want redundancy. You can go in and tell it that you want to do a line with 2 circuits. So you can have 2 separate circuits on that line. That's rare. What isn't rare is trace ratio. So this is if you have a power connection kit at one end of the line and you run your cable all the way to the one end and then turn around and come back. That
Kind of
would
like
be
how we did for those Macrotech manifolds, right?
correct. 100% right. So that's when we go in and we say a trace ratio of 2. So you do that on manifolds that are complex to eliminate T's and splices and junk like that. That's just going to cause you a bunch of headache long term. You also do this on 10-inch and larger pipes. On great big pipes, say you have a 24-inch, you might go 4 passes. You might go 6 passes.
Okay.
So
Yeah, I was going to ask if there was a reason to go above 2.
yeah, great big pipes, you can start going up. And the best way to do it is just model it in here. But 10-inch up to 24-inch, you can get away with 2 typically. But once you hit 24, you're typically starting to talk 4 passes now, unless you're using MI. So there's a little trick. If you had big lines and you're running 4 passes or maybe 6 passes, a lot of times you can do that with 1 pass of MI because the MI's watt density is higher. You can have 30, 40 watt per foot MI. Also, MI is constant wattage. As the pipe heats up, its output just keeps on chugging. Where with self-reg, as the pipe heats up, its output goes down. So there are times to not use self-reg, and that is on higher maintained temperature projects.
Okay.
All make sense?
Yeah, and when we're saying higher maintained temperature projects, are we talking like you have now at 50 degrees as opposed to 40 degrees? Are we talking like 100 degrees because it has something to do with the process?
We're talking 200 degrees to
200 degrees? Okay.
200 degrees to 1,000. So that's higher maintained temperatures. And here's what I'll tell you. Anytime you start to plan a project that has 400 degree or higher maintained, this you may work on other stuff in your career. At 400 degrees, you better really know what you're doing because most high temperature projects end up having a lot of problems. So you want to work with someone that's got 10, 20 years of experience of doing high temperature. I learned a tremendous amount in my 20 years of doing this because I've been involved on projects that failed. They weren't my
Hmm.
designs, they were designs by others. And then I got called in later as to, hey, can you fix this? And I see what they've done. That's why I always jump to 20% up here. And then I really watch right fit technology and some other things. But so as we're filling out this information, it starts picking out what cable you want. So it says S for this 2-inch line, it's got SRL3, and it tells you the cable length to do it with, blah, blah, blah. Here's one thing I'll tell you about SRL3. I personally only use it on 1-inch and smaller pipes.
Okay.
There are times it'll tell you you can use it on 2-inch. Like this scenario we've created, it says, hey, use SRL3 on 2. Well, here's where you get in trouble with SRL3. Everything says it works on this design. What happens with a little bit of voltage drop combined with degradation of insulation? So insulation is at its best the very first day it gets installed. After that, it starts going downhill. People walk on it. They tear part of it apart and don't put it back on right. They remove blankets and don't put them on. Back period, blah, blah, blah. So we did a project 15 years ago for a major semiconductor manufacturer, and they called me up 8 months ago and they said, hey, our line froze up. And so I dissected the design, and someone had done it with SRL3. The actual semiconductor chip manufacturer did their own design, and software said 3, they used 3. And it froze
Hmm.
up. I asked them, send me a picture of the piping. They sent me a picture, and the insulation was literally falling off the pipe. So SRL3 is the only one I really do this with. Anything bigger than 1 inch, I go in here and I bump it up to 5 inch. I mean, I'm sorry, SRL5. So this is
So, can you give a quick explanation of what that number means inside the cable?
I
Like
can.
the 3 versus the 5?
Yep. So SR, self-regulating, L, low temperature, 3 watts per foot, 2 were at the higher voltage threshold. So if we bump this down to 120, you're going to see it picks a -1 cable. If we go to 240, it's going to pick a -2 cable. Now, again, in industrial, we typically mostly work with 277, but you'll have times when they'll run it off some heat trace off of a lighting panel, and you just have to, again, caution them. If you're going to run it off a lighting panel, put in a ground fault breaker, but sometimes we'll see run 120. In commercial, we see all voltages, 120, 208, 240, not as much 277, but they're all over the place. Industrial, we're typically 277 because we can influence it when we do our design. The other cool thing
Okay.
down here is it's kicking out our bill of material, and then if there's any error messages, it tells us there's an error message. Go ahead.
No, that's perfect. Yeah, I figured that those numbers had some meaning to them, but understanding the meaning behind part numbers,
Yep.
is just always useful.
Yep. And I don't expect this meeting right now, Addison, to be your, one and only design meeting. This is a good time for us to go through the software. You get a mile high view at it. And then when you start doing some, what I would encourage you to do is let's do a design review meeting and go through your inputs. What I do when you do that, I always ask you to send me this file first, and then I get the file, I get to look through it, and it makes it more efficient.
Okay.
Um, so let's move on to the next tab at the top here. So we got 4 of them we got to go in and do the same kind of stuff in. Um, so we go in here, and first one's obvious. We pick out what kind of pipe we're using. Is it steel, copper, blah, 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 fiberglass reinforced plastic? Um, and so we get to also pick out the diameter. We got all kinds of diameters in here. I'm going to leave it at 2 inch for now. Then we get to put in the length. The length, let's tell it we want 1,000-foot circuit. Look what it did. It
We
said,
instantly get that error
whoa,
message.
way too long. So if you have 1,000-foot pipe, then we need to realize that maybe we can do it. Maybe we can do it 2 500. Aha, we can do it 2 500s. So now you're going to have this 2 inch line 001-A and a 2 inch line 001-B. So you have to break it into pieces at this point. So this is where you can play around with it. And if it's too long and it's overloading the circuit, or we just don't want to make cables too long, you have other issues that come into play. So just be aware that that's where the error message is going to pop up when you're too long, and you can break them in half or in 3 or 4, whatever it's going to take. You don't run into a lot of that on biogas projects, but we do. I remember I did one, and it might have been Verdi that I had to break some up.
Okay.
All right, fiberglass or insulation. Here's where we get to pick our insulation types, what the customer wants to use, and the thickness. So on the types, by far, the most popular is either fiberglass or minwool. If it's a little higher temp, we're typically into minwool. But if it's freeze protection, it's typically fiberglass. When I got into this business, everybody was using calcill, and you'll still run into it. We really try to talk people out of calcill. It is an old insulation. It absorbs water. If you walk on it, it breaks. And people will tell you, well, we like to use calcium because you can walk on it. Well, you really can't. You're breaking it. You don't even know you're breaking it because it's not crushing down. Like if you walk on a fiberglass line, you can tell somebody's walked on it because it crushes it and it ruins all the aluminum cladding. So we really try to stay away from calcium. And some of these others are really depend on the project. Sometimes projects will require them. Pyrogel is getting more popular. This Dragon Jacket is really cool stuff. It's a insulation that they build up in the panhandle of Idaho, and it comes on site and it basically snaps in place. And so you don't have to have a skilled labor. And it gets designed. They even have an app off of a smartphone. Like if you're doing a skid, you could scan the skid, it goes to them and it creates the design, and then it creates a bill of material. Now, it's not cheap, but it goes on fast. It also holds up really well. It doesn't crush. But let's say you're doing a bridge over a waterway. This stuff is awesome for bridges because it goes on so fast and it holds up really well, so you don't have to worry about it declining.
Okay.
Thickness, I am going to send you an insulation chart that tells you what thickness you should use for each diameter for each maintain temperature. So I'll send you a little chart on that. It's a good rule of thumb. But what I would encourage you to do, like if you're doing a project, and we'll come back to Fresno, California, the chart might tell you to use 2 inch, but you're in Fresno, it doesn't get that cold. You can go in and change it. Like let's say it told you to use 2 inch and use 2. You could go in and see what um, the energy usage. So let's do a electrical report. So right now it's telling us that it's taken 6 amps to run it, 13 amps for startup. Let's go to 1 inch. And now let's go run that same report. So we were 613. We're still 613. No reason to use 2 inch. We can use 1 inch. You go to Nome, Alaska, and you better use the right thickness. So that's where you can play around a little bit, and you can optimize your insulation based on where your project is located. So even though the charts say use 2 inch, you don't always have to follow them. And that's where you test yourself. So do your design, then you can go in and change it down and see if there's much impact on energy usage. There was one project, and I think it was, and I might pronounce it wrong. Is it Veridi?
Yeah.
So Veridi, I think I told them the insulation needed to go up, and then they challenged me, and I went and checked it, and I said, "Oh, you're right. That one it doesn't have a big impact." So it's based on that minimum ambient on where you need to be here. So that's where you can play around with that. Here's a cool thing. When you change a parameter like that, we can do it. We can do global changes in here. So you don't have to go line by line. If you have 142 lines, you have to go in and change every single one. You can go in and do a global change, and then you might have to change a few. But let's bump over here now. Let's say you're working on a project and it's early in the design and the model, the best it is 10% accurate. You can put in a 10% adder. The
Okay.
reason you want to do this is the very first question everybody always asks about a heat management system is how big does the feeder need to be? It's the first question everybody asks. And I always say,
Yep.
well, do you have all the piping designed? No. I said, okay, well, once all the piping's designed, then we can do the heat trace design, but I can't tell you what it's going to be until we design it. Of course, I can't even quote jobs until we design it. So we get asked it all the time. What's it going to cost to do this? It's like, we need to design it. So this is where a line list comes in real handy because you can upload the data into this with a line list. So I'm going to give you a nice pretty one that you guys can use to populate, and then you can just import it right in here. And it's really fast and easy. It'll save you so much time. So anyway, for engineering models, you can adjust it there. Now here's another area where I don't know why we don't default it. The next version will. I always put in 5 feet right here. So this is additional cable. What's this for? That's for the 3 feet that you're going to connect to the power connection kit and the 2 extra feet for the end seal. I always like a little extra in case when you're terminating, the electrician makes a goof and he has to cut off 8 inches of wire and then redo it.
Okay. And then so that extra 5 foot, that's going to be per pipe?
Yep, on each
Okay.
pipe. Yep, because that's what we're doing. Now, up here at the top, this is where we drop in our extra heat sinks. So let's say on this 500-foot pipe, there's a flange every 10 feet. We got to account for those.
Hmm.
So if you're using flange pipe, you got to drop them all in. If there's supports that are touching the pipe and pulling heat out of it, you've got to put those in. And then you account for your different kinds of valves because they all pull heat out. And every time we added those in, I should have showed you this. Let me go back. Let me zero these out. All
Yeah.
right.
Because each one
So,
of those heat sinks is basically just an adder because we've got to do that loop around them, right?
right. So when we add them in, watch what happens to the footage. Maybe it didn't zero out from what I did last time. It should add to the bill of material. Yeah, there's working.
Yeah, there we go.
So it had already added in the one, but and if we got 5 globe valves, you can see the length going up. Now we're getting right on the ragged edge as to how long of a circuit we could actually do. And if I go back and tell it, I don't like that 3 on a 2-inch pipe, I want 5, boom, it just gave us an error message. And that tells us
Okay.
we can't do 500 feet. So we had 1,000-foot pipe. So now I drop it down. We're going to need to do 340s to do that 1,000 feet of pipe.
And so now let's say that, I really want to stick with that 500-foot cable. Can I increase my circuit breaker size to maybe clear that error?
I love it. Yes. Yes. You're thinking the way you should be. I love it. Okay, we're still too long for that. Well, what if we go up on insulation? Will that help us? No, we're still not there. So why are we not there? We're at 24.8 amps. So we're probably a little long on cable. We don't like to run SRL5 at 630 feet. So I think you're stuck. I think you're going to have to do 3 lines.
Okay.
So there is a chart in our design guide that shows you maximum circuit lengths by cable part number. So we're limited both in inrush current, but we're also limited on length of cable, and there's other problems when you go too long with circuits. I'm going to drop this
Okay.
back to 340 as we just keep talking through this. Okay, so we're all back good again. So we got our valves in here, we got our supports, we got our flanges. Although now I can go in and I have to redo these because we don't have that many. Um, and we're going to say we have 3 valves now. It's going to make some changes. So we got to adjust it for that 340 feet. All good on this page?
Yeah.
Cool. Let's go to the next one. All right. So here's where we get into our area classifications. If it's ordinary, you can leave it ordinary. I'm going to dive into this more in a minute. If it's indoor, go ahead and click indoor and it'll adjust the heat loss accordingly. If it's outside, click it out there. Wind speed, you don't need to go any higher than 20. Even if you're doing a project in Wyoming, once we go over 20 miles per hour, it just doesn't impact it. I personally don't even think that should be in here. I think we should just outdoor fix it at 20 and indoor we fix it at 0.
Mhm.
Chemical exposure, leave it at strong oil gas basis for most of your work. If you were doing a water treatment plant or a water plant, then you go in and click mild. What that does is it will change the cable. Oh, the reason it did change it because I had told it to use CT. But normally if you put it in mild, it'll change the jacket from CT, which is a fluoropolymer, to CR, which is a rubber. And that's what
Okay.
that is. But most of the work you're going to do for biogas, you're just going to leave this alone.
And then, so when we're talking about the chemical exposure, we're considering what's inside the pipe.
And what
And
could get
then,
spilled on it.
okay. Because, yeah, I mean, I figure outside, where most of our stuff is, they're probably not walking around and washing stuff down. But if we do have something inside, or, something's running through a storage facility where there's additional chemicals.
Yeah. Yeah,
Okay.
so the only time I would tell you to convert this back to mild water is, let's say it's an acid line on a acid injection system for water treatment. Then you could go down to the rubber. But then you also have to be careful because now you get back into constructability issues and you don't want to
Mm-hmm.
use the wrong product in the right place. So if you don't know, stick with the CT jacket. It's super robust. The guys can drag it on the ground when they're installing it. It doesn't get hurt. Rubber, you have to be a little more careful because you can nick the outer jacket on it. In the commercial world, we use rubber almost exclusively. So when we're doing hotels and you know, data centers, we use a lot of CR. But for industrial, CT.
And then, is there a big price difference, per foot or per 100 feet between the CR and the CT?
Yes, yes. Yeah,
Okay.
that's why in the commercial world they use a lot of CR, and they're not dealing with the strong acids and oils and bases, things like that. But I would just say just be careful what you do here, but be aware there's 2 major jackets in the world: CRCT, CR around water, wastewater, commercial installations. In industrial, we almost always use CT. And a lot of reason for that too is the installers. You get some real hacks out there putting stuff in, and you want to stick with something that's more forgiving. All
Yeah.
right. If you know what's going in the pipe, you can pick what's in it. If you don't know, just leave it water. It doesn't impact the heat loss configurations because those are pretty much all based on surface area of the pipe.
Okay.
All right, now let's move over here because this is where it gets fun. Let's say you're working on a class 1 div 2 application. This is where we want to make sure we don't kill anybody or blow the plant up. I have seen
Hmm.
plants blow up because they don't take this into account. So if it is a class 1 div 2 or a class 1 div 1, this gets real critical that we pick the right product. It's giving me an error message because I don't have the controls selected, blah, blah, blah. Class 1 div 2, I would say design it here first, and then we can move over to class 1 div 1. So,
Yeah. I'm going to say the majority of what we're working with will be in C1D2. I think that there's some very small areas that might be considered C1D1.
yep. Okay,
Um,
so do you know how to know what's what between ordinary C1D2 and C1D1?
Uh, I would say that I have a fairly basic understanding of it. Like,
Okay. So
for
there's only
our
one way
world.
you know. And the way you know is the plant owner Or if you guys are designing the plant, somebody has to create an area classification drawing.
Hmm.
An area classification drawing, while it looks 2D, it's actually a 3D drawing because
Yeah, because it's a bubble.
yes, so it can go up and down. So sometimes you work on a project that has trenches and only the trenches are class one, div one. As soon as you get out of the trench, it's class one, div two, because
Yeah.
the likelihood of having an explosive gas or liquid goes way down. Other plants, yeah, they could have a leak, but it's very rare. So they're only class one, div two. But that drawing is critical. So what I would tell you is don't do a design without an area classification drawing because that's what's going to protect you and minimize risk for your company.
Okay.
So I blew me away. I was up working on a refinery in Salt Lake City, and I asked them for area classification drawing. I went through 10 people, not one of them knew what it was. And they said, we don't have one. I said, you have to have one. Nobody will insure you without it. I took a firm line with them. I said, I won't do your design until you guys can show me an area classification drawing. 2 weeks went by, my phone rang, and the guy's like, holy smokes, we got this. And what an education. Nobody in our whole terminal knew what it was. And yet our whole terminal is class one, div one, and class one, div two. I said, yes, this is why. Because they just go, well, we're going to go just look at a pump and see what the pump is. I'm like, no, I won't design it. I won't do it. I don't want you guys to kill your best friend that you work with by
Yeah.
blowing the place up. And there's a really neat YouTube video. Neat is the wrong term, but interesting would be a better one, of the Exxon refinery in Los Angeles when they blew it up. And I was very near and dear to me because the thing that blew up was called electrostatic precipitator, an ESP. ESPs are used to knock particulates out of the air so they don't pollute. And I sold the job. My company did the ESP, was a prior employer of mine, and we were pretty proud of it. It was one of the biggest jobs I've ever done dollar wise. And it was the most intense project I ever did because it required dual redundancy. So we had to have two complete systems, and each system had to be capable, 200% capable of heating the ESP. And this video will go all into detail, incurring how they blew it up. So they blew up the Exxon refinery in Los Angeles at one time. It wasn't all that many years ago, actually. So there's a reason I'm a stickler. I don't want to be the guy that designs something that kills somebody. I mean, it'd be pretty hard to live with yourself. So I'm a real stickler right here. And
Hmm.
so again, the T rating is either listed on the area classification drawing or an auto ignition temperature will be listed. So either one, it'll either tell you, what T it is. If not, it'll tell you the auto ignition temperature and you can put that in.
Okay. And again, that's something that I'm going to get from my process team or after they do the HAZOP.
Yep. Yep.
Okay.
Yeah. So next one down here is stabilized design, control limited design. This is where you actually design your heat trace circuit so you can't exceed these temperatures. Don't worry about it. If you get into this point, we can go in and look at this, but we are typically going to do our design using a controller. This is where back in the old days, before I had all kinds of these fancy controllers, I used to do some of these. This is going back over 20 years ago. We would design the maximum temperature the system could get by the watt density, the voltage, and the insulation thickness. And then we would dial in the temperature of the pipe that way. It's called a stabilized design. Um,
Okay.
so anyway, don't worry about that so much. Let's just more worry about up here. All right, let's click to this next one. This is where it gets fun. So on the component families, we make a number of series of components. The U series is what we typically sell in industrial. Our options in industrial are U or DL. If you have a very price conscious project, you could use DL. Understand your installed cost goes up a little bit on DL over U series. They're a little harder to install, but they are cheaper. In the commercial world, we use this exclusively. Industrial world, I really try to stick with U series, but just be aware you got two options, DL, U series. U series are far superior. So when we look at the big three heat trace manufacturers, So Raychem, they've gone back to their original name, Chemolex. They use basically a U series. Thermon, they use their own homegrown box with a screw-on lid. I like them and I don't like them. I like them because they're robust as hell. They're expensive. They also require two part numbers to spec. So if somebody's shopping Thermon versus Chemolex, Thermon versus Chromalox, a lot of times they don't realize they're missing one of their part numbers. It takes two part numbers to come up with the Thermon. And if the thing's packed with wire and you screw the lid on, you don't know if you got the lid tight. Also, when you're screwing the lid on, you can sometimes grind away insulation on the wiring and cause a short inside of it. So I'm not a big fan of theirs. I like the Chemolex series, or I like ours. I think ours is the best in the business right now at the U series. To me, it's an investment. This is going to reduce your total cost of ownership because you just don't have problems with these things. They're that good.
Okay.
Power kit options. Back in the old days, before we had lighted end seals, we used to put lights on our power kits. So they would light up when they had power to them. I don't recommend that. I recommend if somebody wants visual monitoring, go ahead and put a lighted end seal on. And so when the heat trace circuit is energized, down at the very end is a light. These come in red or green. In the United States, we predominantly use red. In Europe, we predominantly use green. You can pick whatever color you want, but I like lighted end seals. It gives people a peace of mind. Does it mean the pipe is at the temperature it's supposed to be? No, because you don't know if the insulation's full of water. You don't know if it's been removed, but at least it tells you have continuity. If you have large projects, like you're doing a gold mine in northern Nevada, they use these exclusively because they pull up at a high point in their truck, they pull out their binoculars and they look all around the place to make sure all the lights are lit. So if you're using line sensing full feature set controllers that are coming back to the controller with the temperature of the line, you don't need these. But if you're using a basic system, pretty nice. But if you're
Okay.
having controllers that give you feedback and says, here's what the temperature of the pipe is, you really don't need them.
Makes
Okay.
sense.
We're going to hop over here to control method. And here's where we talk about it. If it's freeze protection, we do a lot of ambient sensing. We just say, hey, how cold is it outside? It's 50 degrees. Bam, whammo, all the heat traces on. However, if we've got lines like caustic lines, we need to keep them at, say, 75 degrees. We've got to put line sensing on. And then we have choices. If it's just one line, we might just put a local electronic controller on. If it is a whole bunch of lines, we might go to a panel. We might do mechanical with a T-stat, but today we don't do a lot of mechanical T-stats. They're kind of going away. The only place we really see them still spec'd are on water plants and wastewater treatment plants. Most people have gone to electronic. Then we can tell it what do we want. Do we want an ITC or ITC2? We can, if we want one that sits on the pipe where we run the heat trace right into it, we can pick a DTS. So the DTS has versus the DTS DC, that has to do with the alarm relay. If your client is daisy chaining all these controllers together with a 24 volt DC monitoring system, which is very common in industrial, then you'd want to order the DC. If you're playing around and they're going to use an AC system, then you can pick this one. If you don't know, pick the DC.
Okay.
If we wanted to have this mounted up on a wall where you look at it and then use a separate power kit to connect to the heat trace, you would just click that. What this does is it changes your bill of material and it's adding an end seal, a power connection kit, and the hazardous controller. If we get rid of that, it just says, no, you're terminating the cable right into this DTS has. And it automatically puts the labels on. You need a label like every 15 feet where the heat trace is underneath. You need the tape to apply the cable. Go generous on the tape. If it says you need 6, order 8. It's
Okay.
something every job runs out of. The pipe straps is how we attach these guys to the pipe. You won't break my heart if you buy them somewhere else, but if it's easier to buy them from us, they're basically hose clamps. But they're not any hose clamps. They're the fancy ones that you get to pull the strap through and then bend the little screw over so they're fast. If you buy cheap ones, you got to sit there and turn to get it to the right size. So just be aware of that. I talked really fast. We went through a bunch of stuff. What would you like to revisit?
Honestly, all of this is good. It's making sense. Um, I guess that what I'm really interested in is how do we figure out, you know, the number of circuits that I need to heat trace my entire plant. Um, I mean, I'm assuming that some of this has to do with whether or not the pipes that are being heat traced are geographically close together or not. And
Well,
then,
no, it really comes down to that line list. So the line list is should be controlled by your process group, and they're going to enter
mhm,
into it the temperatures. So let me do this. Let me just show you one other thing right here real quick, and then let's pull up the line list and go through it a little bit.
okay,
All right, so remember how this line was 1,000 feet long, but we could only do 340 feet?
yeah,
All right, so we're going to go over here and we're going to change the name to A, because we know we got to have more of these.
mhm,
See what I'm doing? I just copied and pasted it. So here's this one. This is now becomes B. Then we click on this one. And now this becomes C. However you want to do your nomenclature. Now we have all 1,000 feet covered. How do we know that? If we go up to the reports and we do a bill of material for the entire project, we're going to see we have 1,300 feet of cable now. So it
okay,
takes every bit of the 1,000, plus it takes an extra 15 feet for your terminations, and then it takes the extra cable for your flanges and your supports and your valves. So that's how we ended up with that. But there's your three UESs, here's your three DTSs, here's all your caution labels, here's all your tape to tape it on. And again, if it calls out 19, I'm going to order 25. And then it's going to call out your 6 pipe straps to attach these to the pipe. And and so, you can just play around with some of this. When I'm doing designs for other people, I click on the detail report and I say, here's all the assumptions we use on these 3 pipes. Now, in this case, they're going to be the same for each 3. But
mhm,
here's all the parameters we use for design. And this is where I take the monkey off my back and put it on theirs and say, I need you to closely review this and see if everything's correct. If not, let us know, we'll change it. Also, we can get our electrical information here. So when they said, well, how much load do I need to power this thing? Oh, you're going to need 51 amps.
okay,
So super cool, right? Oh, okay. Well, I'm doing my own transformer. What size of transformer I need? Well, you need a minimum of 9 kW. So you're going to be buying a 10 kW. So
mhm,
it does your transformer load as well. So these reports are really handy up here. Um, if you want to add a tank, we would come in here and we would insert a tank. And now we've got a tank. And you go through all the same rigmarole. Sizes of the tanks, a whole bunch of information on the tanks. The only thing I'll tell you is if the tank is always full, you can heat trace 80% of it. Most tanks aren't. So typically we only do the bottom third because of that. If you're heat tracing all the way up the line of the wall of the tank, but the tank is a third full, a whole bunch of that heat trace isn't helping you. So we typically design here. Here's what I would tell you is when you do your first tank, drag me into the mix. Let's go through it together because there's some gotchas in here too. So, all right, let me stop sharing this screen and let me go pick something else out now for you. It's taking a minute to load with me again. Okay, so this is the sheet we really like to use. So this is where we would drop in the line number, the drawing number, the rev, pipe material. Rev is really important because I shared with you on one of the projects, they revved it up 3 times without telling me, and then they handed me a rev like Rev 4, and I did Rev 1, but I didn't know what changes were done in 2.3. So I had to go line by line, item by item to see what they changed. Then I got them educated when they did a change, highlight what they changed. And so they're getting better at that. But you'll have to police your own team to make it this a very efficient process. Um,
Yeah, we've had issues with vendors that have poor document control, and it's like every time they send us a new drawing, it's the same rev, there's nothing clouded, and I'm like, guys, come on, please.
Yep. Yep. Well, and I'm just warning you, it happens internally to your company too, because they got me. And then I literally spent 3 hours on a Saturday going because they have to go through and check all this, go through and check all this. So anyway,
Yeah,
you know about document change and how important it is. So here's where we
yeah.
fill in all the stuff. I mean, this is where we put in the numbers, like one ball valve. Are there supports? Additional cable, you can put in your 5 feet there if you want. Insulation type, thickness, the maintain temperature, the minimum ambient, the startup. Here it all is. And then you can import this directly into ChromaTrace, and voila, your heat trace system is designed. And now your buddy that's saying, what size feeder do I need? And what size transformer do I need? You can go, here's the design. You can run that report and send him the report, and you look like a rock star.
Hmm. But yeah, so
So I'm going
going
to
back
send this to you,
to
by the way.
um like those complex manifolds that we just did for Verity, um it like I'm not real familiar with all of the piping aspects of the job yet. So I don't know if it's typical that, these pipes that are being heat traced are generally far away from each other, or if they were next to each other, they would have the same line number.
No, usually every line has its own line number.
Okay. Cause yeah, like that's just where, like with that Macrotech manifold for, um, I guess either one of them, like we had a bunch of pipes and, there was like the one that you did the sketch for. I think that there were 10 of those little cross sections. Um,
Yep.
so, it's like if I just looked at a line list, I would have seen, you know, anywhere from 10 to 20 different pipe numbers, but
Yep. So
assigning each one
that's,
of those its own circuit, then I
yep.
wind up with this giant heat trace panel. Like that seems
Yep.
very inefficient.
Yeah, that's where you have to be able to look at a 3D model or piping isometrics. Today, you guys are all working with 3D models.
Hmm.
Um, but in the old days, we would get a isometric drawing of all that manifold, and we used to design off that. Today, you've got 3D, so you can go in and look at it.
Okay. And so the program doesn't allow me to upload my 3D model and figure all that stuff out for me. That's what I have to do myself, right?
Correct. So I
Okay.
have one competitor that has worked exhaustively to be able to upload 3Ds. And what I can tell you, because I work for them, it's almost as much work to go in and fix what it does wrong as it is just to do it the other way. Line lists
Okay.
are really the best way to approach heat trace. And then if it looks like there's a bunch of little pieces for the manifold, then you got to go in and look at the manifold. And I'm glad you got involved with the manifold. It was an afterthought, by the way. That was not in the original design. That came later.
Hmm.
And and the information was a little pieced together. That's why I sent you that one email that was an email chain. So yeah, I would, get me involved. I'm going to hit one last thing here, and then I'm going to have to jump for another call, but I'm going to send you a follow-up email, and I'll stop the recording. But here's a typical insulation chart. So here's where it shows the thicknesses that you need. And remember, we already visited, can you use 1 inch? Well, in areas where you don't get a real low minimum ambient, you can use 1 inch. Here's the other side of it. We see tanks that are heat traced in 2 inch. You almost never use 2 inch on a tank. You typically use 4 inch all the way up to 6 inch, so 4 or 6, depending on the temperatures. Again, it's all about surface area. Um, and last item, and then I'm going to kill this thing, is can you heat up pipes with heat trace? The answer is yes. How long do you got? You got a month? You got 2 months? If you want to heat pipes up, heat trace is typically not the way to do it. If you want to increase the temperature of tanks, heat trace is typically not the way you want to do it.
Okay. Yeah, that makes sense.
Yeah. All right, so I'm going to stop the recording if I can figure out how to do it. Boom.